All right, let's see how you did on this one. The y-intercept is easy to find because you plug in 0 for x. Take your first derivative, and you can do your sign diagram. And then within that sign diagram, you're going to find out that -2 was a maximum, and +4 was a local minimum. Again, you find the values of those maximum and minimums by plugging back into your original equation. Anytime you're finding points, or anytime you're finding points on your original graph, those values are plugged into your original equation. We plug in test values into our sign diagram into our derivative to find out where it's increasing and decreasing. Once you've got your first derivative, you can find your second derivative. Finding the point where your second derivative is equal to 0 gives the possibility of an inflection point. And in this case, it is an inflection point because it changes from being concave down to concave up at 1, -31. Again, you can find the value of that point by plugging it back into your original equation. And finally, plugging all of these things into your graph. We can sketch it completely. And I've labeled 0, -5. Now those red points that are the x-intercepts, again, unless you can factor the original equation, those you would have to find with a graphing calculator. Although there is a formula for solving cubic equations. You know how there's a quadratic equations formula?
I saw it. It ain't great.
It is not the nice looking formula. I mean, when you learned the quadratic formula and you saw it like -b, it's got a plus or minus and a square root, you felt like that is the most ridiculous, ugly looking formula ever. Now, you're like, it's pretty easy. It's not bad. Here, I'll find it for you. Here, I'll put it on the video for a second so you can admire it later. This example I included because it's a little bit different. It's a little bit different because when you start off, again, we're going to find all stationary points and inflection points. What we've been doing all the way along is starting with our derivative. It's going to be bring the 2/3 out in front, gives you x, 2x to the -1/3 minus 1. There's our first derivative. Setting our first derivative equal to 0, I'm going to change that -1/3 to a cube root of x on the bottom. Setting that equal to 0, moving your 1 over, multiplying both sides by the cube root of x, and cubing both sides gives us x equals 8. So we have a critical point at x equals 8. So I'm going to put 8 on my number line. I'm going to plug in a value bigger than 8 and smaller than 8 and see what happens. So you're going to plug in 10, go to your derivative. The cube root of 10 is a nice number. Thanks for picking 10. That's a great number to choose. 27. That seems like a better number. So if I plug in 27, the cube root of 27 is 3. 2/3 minus 1 will be negative. So choosing something bigger than 8 means my function is decreasing. Okay?
We don't do that here.
So now let's choose a number less than 8. Let's choose 1. Right? Cube root of 1 is 1. 2 over 1 is 2 minus 1 is positive. So it's increasing. Perfect. Everything seems good. Okay? Except someone else says, I chose -27 as my number. Oh, okay, well, let's try negative. It's less than 8. So -27 This will be negative 3 when you cube root it. So negative 2/3 minus 1 is going to be a negative number. And they said, well, I got a negative here, so shouldn't this be decreasing? So it's increasing and decreasing at the same time? How does that work? Why do we have a problem?
Below 0.
It's below 0.
It's an asymptote at 0.
Why is there an asymptote at 0? It can't divide by 0. So we know that we can't divide by 0. But in our original equation, 0 is fine. Look at our original equation. Right? I can plug in 0 for x, and I get 0 for y. I've got a point, 0, 0.
Okay, we talked about this like last year too. Like when you can plug into the original one, but like you can get the point. But like if you plug it into like the change one, and you're still dividing by 0.
But here, we've got a non-permissible value, x can't equal 0, but that non-permissible value isn't for the original function. It's a non-permissible value for our derivative. So what happens is when we're writing our critical values, we have to include not only non-permissible values of our original graph, but we have to also include non-permissible values on our derivative graph. And the fact that there's a non-permissible value on our derivative graph means at x equals 0, there is no derivative. Okay, so how does that show up on the graph? Someone told you, so you've seen what it looks like. Nice. Way to ruin it for everyone. No. Okay, let's see. Let's keep going here. Let's do our inflection points as well. So if I did my second derivative, that negative 1/3 would come out in front. If I set that equal to 0, well, this is equal to negative 2 over 3. I move that x down here. This is the cube root of x to the 4. Is this ever equal to 0? No. The only time a fraction is equal to 0 is if the numerator is equal to 0. But we still have a non-permissible value at 0. Yeah, the dividing by 0 pictures. Love that picture. But in this case, when you have that x to the 4 inside the cube root, that's always going to be positive. Oh, that doesn't look like a cyclops. There we go. The negative cyclops and the negative cyclops. It's always concave down. This is a weird function, supposedly. Okay? We've got a local maximum at 8. So let's figure out what that point is. We can plug in 8 into our original function, which is going to be 12 minus 8, 8 comma 4. We have that as our point. We know where it's decreasing. We know where it's increasing. We know its shape. And we know something bad happens at 0. And we also know that it's always concave down. Two, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Let's label that point. 8 comma 4. That's a local maximum. Okay. We know that we have the point 0, 0, because that was our y-intercept, our x-intercept. When we plugged in 0 for x, we got the point 0, 0. We know that our graph between 0 and 8 has to be increasing and concave down. Okay, that would make sense for that.
That being open only 0, 0?
What's that?
That being open one because it doesn't ever go to 0?
Well, 0 exists. 0 still is a point on our original graph. So we just know that the derivative doesn't exist. So what does it look like if the derivative doesn't exist? And now it's decreasing. It's decreasing after this. I don't know, that might be a little short, but I was going to run into the side of my smartboard, so I had to quickly turn it. Okay? If we wanted to, we could see if we could find another x-intercept. Okay, if I wanted to see where does this point happen, I could set my original function equal to 0, which is 3x to the 2/3 minus x. We already know that 0 is one of our answers, so I can factor out an x. What would that leave me with? 3x to the negative 1/3 minus 1. Setting this little part equal to 0. So this is 3 over the cube root of x minus 1 equals 0. Move the 1 over. Can I move the 1 over and multiply by cube root of x at the same time? Is that too much in one step? And then cube both sides. So we get x is equal to 27. Obviously, this is not to scale because that's 8, and that goes all the way to 27. Yeah, maybe. It's a bad scale. So now on this part, okay, it needs to be decreasing. 0 seems like it should be a local minimum. In fact, according to this, it is a local minimum, even though our function doesn't have a derivative at that point. So what does that look like? And it has to be concave down. So it has one of these kind of sharp points, and the reason the derivative doesn't exist because I can draw this tangent, this tangent, this tangent. I can draw a whole bunch of them at that point. Ooh, it kind of looks like it exploded when it hit the x-axis there. I like that. Yeah, and it you just missed the most important point. Like, yeah, and then boom, you missed it. Yeah, so.
I see an exploded graph at 0.
So we have a cusp at that graph. I think that's the name for it. A cusp technically is when, if those curves would continue, the tangent would be perfectly vertical at that point. I'm not sure that this necessarily follows that definition perfectly. But we have everything concave down. 0, 0 is still a local minimum, despite the fact that we can't take the derivative at that point. So we do have a little bit of an interesting graph.
How do you know the shape will be whatever you want?
How do I know the shape is? Well, it has to be going down, and it also has to be concave down. And so in order for both of these to be concave down, you get a sharp point at the bottom.
Was it just also like, because part of the definition of a minimum is that it has to, the tangent has to be like flat. Technically, you can kind of say it is flat.
You could draw one of them that's flat.
Yeah, one of them's flat.
So it's still a local minimum, because if you would check on either side of 0, that's the smallest it gets.
The way you'd say that the derivative is undefined is because like it has more than one tangent. So
Yeah, like I can draw, that's what I was drawing with the red lines there. I was trying to say, I could draw so many different tangents, and since it's undefined because there's not one for sure that fits that. So then we say it's undefined when we can't say one answer for sure.
There's, last semester you had one, I forget, where you were showing that you could prove that it was a power or something where the power rule of zero or negative, when you can prove it two different ways.
Right.
Couldn't you
Yeah.
use the same sort of logic, right? If the slope is here, here's how the slope changes.
Yeah.
Thereby working backwards, this is how the slope would be. Why can't you use that sort of logic?
Because the slope can be anything.
Because the slope could be anything at that point. Okay. So an interesting graph, to say the least. And yet, this is a continuous function. There's no non-permissible values in here. And so if you would take, what's the limit as x approaches 0? It's 0.
As x approaches infinity.
As x approaches infinity, the x to no, it'd be negative infinity. Because this x is the highest power, it's subtracting x. That's more powerful than the x to the 2/3. Doesn't matter. Three's just little. All right, here is our, oops, that's not the one, that was our old quiz. No, that's our old, did I delete it?
Yeah, it's going back to blue.
No, it's here. This is the one. Okay, here's our last question. I know we've only got a couple minutes, so I'll put it up on the video. Show that this does not have an inflection point. So you take your first derivative. You get 0. Okay, it tells us that it's a local minimum. You do your second derivative, and you get x equals 0. And this is, again, trying to point out that it is not enough to just get your second derivative equal to 0 to say that it's an inflection point. When you do your sign diagram, both sections are concave up. Okay? The other way that you could say that x equals 0 is not an inflection point, it's only an inflection point if your first derivative also stays the same sign at that point. So the fact that we go from negative to positive at 0 in our first derivative test tells us that this will not be an inflection point as well. So if I want to write a really long-winded answer for this, I could. F of x does not have an inflection point because the only place where the second derivative is equal to 0 is at x equals 0, but I say it's concave up before and concave up after. I like that explanation best. But you could also say that the first derivative has to stay the same sign at that point, and it doesn't. So there are no inflection points. You just said no.